So how did you set it? 1 pound of methane, CH4. Okay, then convert it to grams, 453.6 grams per pound. And then what? Yeah, what's the molar mass you got? 16.042. Don't go to more than 2 decimals, it's a waste of time. So what did you use for carbon? I would use 1201. For hydrogen, do you use 1008 or 101? Okay, if you use 1008, you would use 108 if you're dealing with atomic hydrogen or H2. You know, then use 1008. But if you're dealing with hydrogen inside a compound, I'd just use 101. It's not going to make that much difference, and it'll save you a lot of time. Because these molar mass calculations, they can be time consuming, and you got a lot of them to do. And so what works good is just having 4 sig figs. So 101's okay, so I get 1605. I just do that. It's off a little bit. Yours is more accurate, yours is better, but yours also takes a little more time to calculate. These you can calculate in your head quite quickly. So you get 1605 grams of methane per mole of methane. That's a big advantage, being able to calculate in your head. Like, I mean, I already see 1605, 3200, 4201, 1802. You know, I can do these in my head because I just go 2 decimal places. You know? And then what? Okay, what is it? 1 to 1? Yeah, this is just a 1 to 1 mole ratio. We still have to write it in here, otherwise the units don't cancel out. So 1 mole of CO2 for every 1 mole of methane. So it's a 1 to 1 mole ratio. And then what was the molar mass you got for CO2? 44.01 grams of CO2 per mole of CO2. And then we'll just do, what, pounds? 1 pound is 453.6 grams. So this gives us 4 sig figs, 4 sig figs, 4 sig figs, 4 sig figs. How many sig figs do we have here? Well, you know what I'm going to do? I'm going to call it exactly. And exactly 1 pound of methane, how many pounds of CO2 would we generate? So I can get that answer to 4 sig figs because everything has 4 sig figs. And so if I say exactly 1 pound, so we're going to assume this. In exactly 1 pound of methane, approximately how many pounds of CO2? And so I'll do, well, I got 453.6 divided by 453.6. I'm going to not even bother with those. So I'm just going to take 4401 divided by 1605. So 4401 divided by 1605. And I get 2.7420 pounds of CO2. And so if I burn exactly 1 pound of methane, I'm going to get approximately 2.742 pounds of CO2, or about 3 pounds. So that, you're right, that's good. Or I could treat this as 1 sig fig. If I treat it as 1 sig fig, then this is around to 3 pounds. So for every pound of methane, I get about 3 pounds of CO2 less. All right, this is what we call the theoretical yield. Theoretical yield. Sometimes we don't get the theoretical yield. Like maybe we might form a little bit of carbon monoxide, or sometimes we might lose some. If we try to capture that CO2, we might lose some. So this is what we call the theoretical. Theoretical yield is the yield based on stoichiometry. Based on stoichiometry. There's something called the actual yield. The actual yield is what you actually get. You know, and sometimes it's off a little bit because of other factors. Maybe some soot is formed, maybe some carbon monoxide is formed, maybe you lose some, you know, this kind of thing. exact same problem, except now it's not going to be in air. It's going to be confined in a container. So what we're going to do is we're going to mix the oxygen and the methane together. Now, if you do it out in the open lab, air, we got plenty of oxygen. But if you do it in a confined container, there's a limited amount of oxygen present in there. So let's say you're burning methane in a submarine or something like that, you're going to have a fixed amount of air there. And you got to start worrying about, you're going to burn through the oxygen. And so let's say I'm going to do this. I'm going to mix together, let's mix together, let's take 115 grams of methane plus, we'll go 150 grams, let's go 150 grams of oxygen. If I now I have a limited amount of oxygen, is it enough oxygen? Maybe you can tell right off. Maybe you can't. But do we have enough oxygen to burn it? Or do we still have plenty of oxygen to burn it? And so the question is this: how many grams of CO2 will I produce here? Now, when we're given more than one quantity, when we're given multiple quantities, then that automatically categorizes this as what we call a limiting reactant problem. Limiting reactant problem. One of these reactants will run out before the other, unless it's what we call stoichiometric. If it's stoichiometric, if you do this stoichiometrically, that means you're adding just the right amount of methane and oxygen. And so what is just the right amount? Well, just the right amount would be for every mole of methane, I want to just add 2 moles of oxygen. And that is stoichiometric. That's perfect. But does everybody have enough time to measure it exactly? Like say I need to burn a pound of methane. I'm going to measure the amount of oxygen I'm going to put in there exactly so it's perfect. It's stoichiometric. Is anybody going to do that? No. What people will do is I'm going to burn a pound of methane. I'm going to add plenty of air. I'm going to make sure there's plenty of air there. In fact, I'm going to make sure there's too much air. If there's too much air, then all the methane will burn. But however, if I don't have enough air, what's going to happen? All the methane won't burn. And have a problem with that. And so whenever we're given quantities, multiple quantities, then the other quantities aren't in excess. If we're only given one quantity, for example, if we're only given 1 pound of methane, then we got to assume we have plenty of oxygen. Otherwise, it doesn't make sense. So if we're given one quantity, we assume all the other quantities are in excess and we have plenty. However, if we're given multiple quantities, we can't make that assumption. One of these, or it might be stoichiometric, we don't know. If it's stoichiometric, then it's perfect. But in all likelihood, people aren't going to waste a lot of time trying to make it perfectly stoichiometric. Somebody's going to add more of one than the other by accident or by design or purpose. And so what we're going to do is this. We got to figure out which one we have too much of and which one we don't have enough of. And the one we don't have enough of is called the limiting reagent. The one we have too much of is called the excess reagent. So one of these is limiting, the other is in excess. Now, it could be stoichiometric, so if it's stoichiometric, then there is no limiting, there's no excess, it's just the right amount. But that's rare, that it's stoichiometric, because it's hard to measure out. And so you just measure this out, and that's what you get. And so the method for solving these problems is this. We're going to use the smaller amount of product method. The smaller amount of product method just says that, okay, what we're going to do is we're going to calculate the theoretical yield of product from 115 grams of methane. And then we're going to calculate the theoretical yield of product from 150 grams of oxygen and see which one yields the smaller amount of product. So, step one, okay, calculate the yield from 115 grams of methane. Okay, so we just did the stoichiometry, 115 grams of methane. We're going to do gram to mole conversion. So mole of methane weighs 16.05 grams. And then mole to mole, it's a 1 to mole ratio, 1 mole of CO2 for every 1 mole of methane. And then CO2 is 44.01 grams per mole. So let's see what that yield is from my calculator. So 115 divided by 1605 times 4401. 315.3 grams of CO2. I'm only allowed 3 sig figs here. Okay, B. Next, I'm going to calculate the yield from 150 grams of O2. So we'll go with 150 3 sig figs grams of O2. And then a mole of O2 is 32.00 grams. And then what's the mole ratio between O2 and CO2? Looks like for every 1 mole of CO2, we need 2 moles of O2. It's a 1 to 2 mole ratio. Then 44.01 grams of CO2 per mole of CO2. So let's figure that out. 150 divided by 32 divided by 2 times 4401. 103.1 grams of CO2. So the way that people think of limiting reagent is they think of it in terms of let's say bicycle tires or something like that. Anyway, let's say to build a bicycle, you need 1 frame, bike frame, and 2 tires. So 1 frame and 2 tires. Right? And you're going to weigh them. So a frame weighs this much, bike tires weigh that much. So when you look at it, by the numbers, it's easy. 1 frame, 2 tires. But when you look at it by mass, it's difficult because we have this many grams of frames and this many grams of tires, so it's a little bit abstract. But basically what this is saying is this. This is saying I can build this many grams of bicycle from this many grams of tires, and I can build this many grams of bicycles from that many grams of frames. So in other words, here, I'm going to run out of oxygen. What's going to happen is I'm going to eat up through all my oxygen, and I'm going to build this many bicycles, and then once I eat up through all my oxygen, I have no more oxygen left. So I can't build any more CO2 molecules. And so the smaller amount method is this. I can only make this amount because I don't have enough oxygen to build this amount here. So this is what we call the theoretical yield. I need more oxygen if I want to burn all my methane, so not all my methane is going to burn. So this is the theoretical yield. That means I'm going to have leftover methane. And so the methane is going to be called the excess reagent. And the oxygen is going to be called the limiting reagent, the reactant. And so the oxygen is going to limit how much methane is combusted. And the smaller amount is the theoretical yield. This is the smaller amount of product. Which is the theoretical yield. And so let's say, you know, I have this. I have 30 frames, but I only have 20 tires. If I have 30 frames and 20 tires, how many bicycles can I build? Well, each bicycle requires 1 frame and 2 tires. And so how many bicycles can I build? Well, 30 frames means I could build 30 bikes, right? Because each bike requires a frame. So 30 frames means I could build 30 bikes. How am I going to be able to build 30 bikes? Why not? Because I don't have enough tires. 20 tires means I can only build how many bikes? 10 bikes. And so there's no way I'm going to build 30 bikes. So 30 bikes is out. I'm going to just build 10 bikes. 10 bikes is going to be called my theoretical yield bikes. And that means all the tires are limiting. I'm going to use up all the tires. It's going to be completely consumed, but I'm going to have some leftover frames. In fact, I'm going to have 20 leftover frames. See that? So this is what we're doing here. So limiting reagent, we're going to completely consume this, but we're going to have leftover. But we're going to have leftover, some leftover. Now here we can figure out how much left over, because if we build 10 bikes, then we started off with 30, we're going to use up 10 of those frames, and we're going to have 20 frames left over. Well, we could do the same thing. How many grams of methane remain unreacted? And so that's what we're going to calculate. The grams of excess reagent left over. The grams of excess reagent left over is equal to the initial grams minus the amount consumed by the limiting reagent, the LR, we'll call it. And so the initial grams was 115 grams. And then out of that 115 grams, how much was consumed by the limiting reagent? The amount that was consumed by the limiting reagent, we do another stoichiometry calculation. So this will be our third stoichiometry calculation for this particular problem. Here we're going to start off with the limiting reagent, which is 150 grams of O2. And then we're going to convert that to moles. So a mole of O2 is 32.00 grams. And then we're going to get the mole ratio. And this is going to be grams of methane. And so what we need to do is we need to go from moles of O2 to moles of methane. And so it's going to be a 1 to 2 mole ratio. 1 mole of methane for every 2 moles of O2. And then from moles of methane, we're going to go to grams of methane. So 16.05 grams of methane for every mole of methane. And so this is the same thing we could have done here. The number of frames left over, is equal to the initial. The initial is 30 frames minus the number consumed by the limiting reactant. The limiting reactant is 20 tires, so the number consumed would be 20 tires, or wheels, or whatever, 20 tires, and then we have this ratio. We have 1 frame for every 2 tires. And so this is going to give us 30 frames minus 10 frames, and I get 20 frames left over. Well, it's the same thing we're doing here. So this is going to give me 115 grams of methane that I originally had, minus, okay, now we have to do this. This is a new stoichiometry. This stoichiometry calculation is not the same as this, and it's not the same as this. It's a little different. Because I'm going from O2 to methane. This one was methane to CO2, O2 to CO2. This one is O2 to methane. So 150 divided by 32 divided by 2 times 16.05, 37.61. I'm about 3 sig figs here. Grams of methane. Minus 150. 77.38. 77. Well, I'm only allowed 1 decimal place, so 77.3. So it's going to knock me down to 2 sig figs. 77.3 grams of methane unreacted. That's a lot of leftover. The leftovers are usually a waste time. So in this case, I didn't have enough oxygen. I need a lot more oxygen. Burn. Just didn't have enough oxygen. No, that's a limiting reagent type problem. Now, this is what we call theoretical yield. You should be able to build 10 bikes, right? But let's say, in theory, you should have been able to build 10 bikes, but for some reason or for some other reason, you only built 9 bikes. If you only build 9 bikes, then what you have is like a 90% yield. And so the theoretical yield is calculated based on stoichiometry. You know, if we're only given 1 reactant, then we assume the other is in excess. If we're given 2 or more reactants, we do this, and then we get the theoretical yield. But sometimes we don't always get the theoretical yield for some reason. The theoretical yield is called the ideal yield here. It's the amount of product formed from the complete conversion of the given amount of reactants and products based on stoichiometry. The actual yield is the measured quantity determined by experiment or experience, lower than ideal yield typically. It's a result of impure reactions, incomplete reactions, side reactions, etc. So we have something called percent yield. And so maybe a bike was stolen or something like that, and you got less than 10 bikes. You're supposed to get 10 bikes. Or maybe some wheels were bent, or tires were bent, or the frame was damaged. You get less, something less. That's after we calculate the theoretical yield. And so a solution containing 3.18 grams of barium chloride is added into a second solution containing excess sodium sulfate. So this is typically, typically we're interested in reacting one completely, and the other we can keep in excess or slight excess, because it's hard to measure out things stoichiometrically. Okay, calculate the theoretical yield. I'm not going to call it ideal yield because ideal is not as precisely defined as theoretical. Like the term theoretical yield. Theoretical yield is what's used in Chem 1A and Chem 7. So I must use that. So barium chloride, what's the formula for barium chloride? BaCl2. is added to the second solution containing excess sodium sulfate. What is sodium sulfate's formula? NaSO4. Right. So what's the charge on sulfate? What's the charge on sodium? It doesn't match. If SO4 is 2 minus and sodium is plus 1, then I need to, it's got to be Na2SO4. Barium sulfate, well, this is another double replacement. So we're going to form barium sulfate and sodium chloride. Barium sulfate, what's the formula for that? BaSO4. And sodium chloride, what's the formula for that? NaCl. So sulfates are soluble, except for silver, lead, mercury, calcium, strontium, barium. So this is one of the insoluble sulfates. All the other sulfates are soluble. And sodium salts are all soluble, so that's aqueous. So we need to balance this. One barium, 2 chlorides, we'll need 2 sodium chlorides, and then it's balanced. So we're going to start off with 3.18 grams. 3.18 grams of barium chloride. Then I'm just going to go grams to moles because we want to get to the heart of stoichiometry. The heart of the stoichiometry is the mole-to-mole conversion. So we go grams to moles of barium chloride. And then we can go wherever else we want. Calculate the theoretical yield of barium sulfate. So we need to go to barium sulfate next. So we'll go from moles of barium chloride to moles of barium sulfate. From moles of barium sulfate, we're going to go to grams of barium sulfate. And so this is assuming we have excess. You know, if it's not specified, like sodium sulfate, then we're going to just always automatically assume there's excess. If this is specified, then that changes the type of problem. If the amount of sodium sulfate were specified, then we would call it what type of problem? We'd call it a limiting reagent problem, and then we'd have to solve it using the smaller amount of product method. But since only one reactant was specified, then we can safely assume that this is going to be an excess. So we got excess, XS, which is abbreviated excess in chemistry. So we're going to need some molar masses. So let's take a look, periodic table. Barium. Barium's pretty heavy, 137.33. Barium. 137.33. Chlorine is 35.45. Sodium. Sodium is 22.99. 22.99. Sulfur, 32.07. And oxygen is 16.00. So let's do barium chloride first. So barium chloride is going to have 2 chlorines and 1 barium. So let's go ahead and add those together. 2 chlorines is 70.9. 70.9 plus 137.33. 208.23. 208.23. Then, actually, I didn't need sodium and chlorine, did I? No, I didn't. I'm doing barium sulfate next. Actually, I didn't need these. So, 4 oxygens. So it's 4 times 16 would be 64, plus 3207, plus 137.33, 233.40. Is it time? Almost. So we'll just finish this setup here, please. So we got 3.18 grams of barium chloride. And then where do we go from here? We're going to go from grams to moles using the molar mass. So 1 mole of barium chloride formula units. Barium chloride is an ionic compound, so we wouldn't say molecules, we'd say formula units. 1 mole of barium chloride formula units weighs 208.23 grams. And then where? Mole-to-mole conversion. And what's the mole ratio? Well, it's a 1-to-1. So 1 mole of barium sulfate is produced for every 1 mole of barium chloride that reacts. And how much does barium sulfate weigh? Barium sulfate weighs 233.40 grams per mole. Sulfate. So let's go ahead and calculate this. 3.18 divided by 208.23 times 233.4. I get 3.564. I'm allowed 3 grams barium sulfate. So in theory, this is what we say. In theory, if I take 3.18 grams of barium chloride and react it with excess sodium sulfate, I should precipitate out 3.564 grams of barium sulfate. This is my theoretical yield. That's how much I should precipitate out. Now, if I try to capture that precipitate, I'm going to filter out that precipitate and weigh it. Like, in theory, sometimes you have losses. Like, for example, let's say you're making a cake or you're making cookies or something. What happens is, if you start off with this many grams of ingredients, do all those grams of ingredients end up on the cooking sheet? So for example, do you scrape off every single piece of dough out of the mixing bowl, or do you leave some behind? Do you lose some, or do you, I don't know how you work, but I leave a lot behind. And so, in theory, yes, but in practice, it's not worth the time to scrape every single atom of cookie dough out of the mixing bowl because it just takes too much time. And this is what happens in chemistry. To get every single last bit of barium sulfate out of your test tube sometimes isn't worth it. And so sometimes in practice, you end up with less. And that's what we call the actual yield. The actual yield is, well, it depends on how much time you want to spend. Sometimes it's out of things that are out of your control. Sometimes things are out of your control, like side reactions or what else happens. So in theory, we should have gotten 3.564. In actuality, they lost some. They left some behind in the test tube. Maybe, it's too hard to get out. They lost some. And so this is the actual yield. The actual yield is typically less than the theoretical yield because they lose some. Sometimes when you take organic chemistry, you might get an actual yield that's higher because it's contaminated, it's grossly contaminated, Sometimes that happens as well. And so, of course we want 100% yield. We want to get, actually what we want to get is this much, but sometimes it's not worth it. And so we calculate something called the percent yield. The percent yield is the actual yield divided by the theoretical yield times 100%. And so these people only got 3.37 grams, they lost some. And so we do 3.37 grams. In theory, they should have gotten 3.564 grams. And so what was their percent yield? So let's go ahead and do that calculation quick here. Do 3.37 divided by 3.564 times 100. 94.55. 94.55% yield. In other words, they got a 94.6% yield. 94.6% yield means they lost 5.4% of the product. They lost it by things that maybe were in their control, or they lost it by things that were out of their control, but they lost a little bit. Obviously, we want 100% yield. We want to get, what we're supposed to get in theory. But, the book got 94.7%, rounding, I think. Or differences in mole mass. Whichever. Okay, we'll stop here. We're going to take a break and then we'll continue.